Well, hello, anatomy students. So Mrs. Shelton here for your second lecture on your special senses, chapter 10. Today, what I want to talk to you guys about is your section 7 and section 8 on hearing and equilibrium. Now, with this particular section, the first thing I want to make sure that we are clear on, because with hearing and equilibrium, we are now, again, we're moving on to our special senses. These are not somatic senses. Hearing and equilibrium, we should be aware of, is all a part of the receptors that are mechanoreceptors. Mechanoreceptors respond to motion or movement. So this is what your hearing and your sense of balance are actually responding to is motion. So in order to think of hearing, that your brain, so your receptors are responding to motion, we do need to understand a little bit more about what the heck is sound. So, because we know that that's what hearing is, your body is detecting sound, and we need to talk about all the organs that are responsible for that. But we've got to understand what sound is first. And what sound is its vibrations and molecules. So, what you're hearing from me right now is actually the air molecules that are actually doing this, what I like to call a molecular mosh pit of compressing and rarefacting. So, they're squishing together and then they are expanding out, causing the next group of molecules to compress and then expand back out and then cause the next one. So it ends up creating this wave-like motion of vibrations and molecules. Now, when we talk about these vibrations, they actually have a frequency to them. How fast they're actually compressing and rarefacting is frequency. That's what we would also associate with sound as pitch. So if you go to an up high key, that means that my molecules are vibrating at a faster rate, or I go down to a low, my molecules are vibrating at a slower rate, is what that frequency is or that tone is. Now, when we talk about something being loud, it's how many molecules are we getting to vibrate or compress and rarefact is what's actually happening. So do recognize when we talk about this term frequency, you will do a hearing test on your activities page that sees what frequencies you can actually detect. We don't want it to be too loud though, because we will talk about how amplitude or loudness can actually lead to some hearing impairments with you too. But that's the basics of what sound is molecules that are compressing and rarefacting. Now, can you hear if you were out in a vacuum, if you were out in space? I don't mean a Hoover. I mean a vacuum, which is there's no molecules. There's no way for sound to be transmitted that way. So that's how sound has to travel, is through this series of compressions and rarefactions. And how quickly they're compressing and rarefacting gives us that different tone or that different pitch that we detect. So here's a diagram of your ear. You need to know every single part of this structure because they are all really important for detecting your sense of hearing and then also your equilibrium, which is your sense of balance. So with this, make sure that you are identifying, label every single part here, but let's talk about each one and what they actually do. So out here on your auricle, so your auricle is actually for collecting those sound waves and funneling them to what I like to call the ear hole. It's this obnoxious name called your external acoustic meatus. But this auricle, if you actually needed to hear better, you can actually give yourself just bigger auricles and you can then funnel in more sound waves into this external acoustic meatus. Now, all that's happening here are those sound waves are being funneled then to your tympanic membrane, also known as your eardrum. I need you guys to know it as your tympanic membrane. Is why it's called an eardrum is because it vibrates. And so those compressions and rarefactions of molecules cause the eardrum to vibrate, and it's just a little bit. But what's attached then to the backside of that tympanic membrane are these three inner ear ossicles. These are the three tiniest bones of your body. There's the malleus, and the malleus being connected to the tympanic membrane is going to vibrate just a little tiny bit. The incus then, the second bone, well, this is going to vibrate just a little bit more, and then that's going to cause this stapes. This bone here, the stapes, is now going to vibrate just a little bit more, and it's actually then vibrating against this structure called the oval window. So it's kind of like this is banging on this glass of the cochlea. The cochlea is where our nerve endings for hearing are going to be located. So here in this cochlea, it kind of looks like the body of a snail. The cochlea is where we hear, but then this structure up here, there's these three half circles. Ha ha ha, semicircular. These are semicircular canals. This structure up here, this is for your sense of balance or your sense of equilibrium up here. But this whole structure in here is going to be responsible for hearing and also for equilibrium as well. But it's the cochlea where our organ of Corti is going to be located and where our sense of hearing is detected. And then once those nerve endings receive that those mechanoreceptors receive that motion of change, it's actually going to send that signal out the cochlear nerve, which in our diagram, the vestibule is for your sense of equilibrium up here. And we'll talk more about the vestibular structure up here. Cochlea is going to be for your sense of hearing. The nerve in our textbook is referred to as the vestibulocochlear nerve combined. And that's just the way that I need you guys to know it at this particular point. Now, there's another region here that I do need you guys to be aware of. There is, your textbook calls it the auditory tube. I need you guys to actually change that and know this as the eustachian tube. And that's one of the questions on your reading guide that I ask you about. You call it a eustachian tube. This eustachian tube is actually responsible for balancing air pressure from this middle ear to this external ear. So you guys know that when you travel up to high altitudes or low altitudes, you yawn. Well, that change is because as you go up to higher altitudes, well, there's fewer air molecules that are in this space here compared to here. So there's more pressure pushing on your tympanic membrane. So now if you yawn, well, what that ends up doing is this tube opens up to your pharynx, the back of your throat. And so now that allows for gas pressure equilibrate between both of these sides of your ear and relieve that particular pressure. Now, some of you guys ended up having tubes in your ears when you were kids because you got chronic ear infections. Ear infection actually exists back here where now there's bacteria that's trapped here because these eustachian tubes oftentimes after sickness get clogged. And so it can't drain and bacteria then just has a party in this space in your ear. But those are some of the parts of your ear that you should be familiar with and be able to identify. Here's actually a really cool picture of your auditory ossicles, these three bones. So these are the three tiniest bones in your body. Kind of fun fact is through evolution, these did not originate in evolution as bones that helped for hearing. They were actually part of jaws of previous organisms. Now, in this particular diagram, I need you guys to make sure that we're seeing kind of the cut open view of the cochlea and also of your semicircular canals. Now, paying attention to the fact that what is inside this cochlea, so this ends up being this tube that's coiled around, it is filled with a material that is called endolymph. So this endolymph is this jelly-like goo. But this is really important for being able to transmit sound from that tympanic membrane all the way to the nerve endings. Now, also in my semicircular canals, there's also endolymph in there too. So it's this movement of this endolymph that is ultimately going to be sending signals through our vestibulocochlear nerve. So here's my vestibular nerve, here's the cochlear nerve. They do actually have a separation, but again, like I told you, vestibulocochlear nerve is just fine to make sure you understand. Now, for our sense of hearing, where our nerve endings are for our sense of hearing. So inside that cochlea, that tube that is just coiled around, there are these nerve endings here that are actually referred to as hair cells. Now, this full structure where all of these hair cells are located is called the organ of Corti, probably named after Dr. Corti, who discovered it. Like any good doctor, they name it after themselves. But what you can see through this is there is this endolymph that actually rests on top of these hair cells. So what ends up happening with our sense of sound is we have our sound waves that vibrate the tympanic membrane, get amplified through the auditory ossicles, and then that stapes on that oval window starts vibrating the endolymph, and it's the endolymph vibrations that then get detected by these hair cells. And we have different hair cells that detect different frequencies, and then a number of hair cells that are getting vibrated at that frequency all contributes to that sound that we ultimately hear. But that's your organ of Corti, which is inside the cochlea, which is our organ for hearing. Here's an electron microscope picture of the hair cells in that organ of corti, which is pretty cool. It looks like little brushes, is what it looks like. Now, in talking about equilibrium, so with equilibrium, we're going to talk about static equilibrium and we will talk about dynamic equilibrium. And so with our static equilibrium, static means we are staying still. Now, even if you were sitting still and somebody now just picked you up and hung you upside down, your brain would know which direction you were facing. So you're not moving, but now somebody else is, because in the vestibule, so the vestibule is this space right in here, the cochlea. What we end up having is we have rocks in our brain. So you have rocks in your head. It's not in your brain. It's actually in the vestibule of your semicircular canals. There are these little rocks called otoliths. So these otoliths, what they are going to be doing is moving with gravity. And so as you tilt your head forward, or as your head tilts backward or to the side, these otoliths actually move with gravity, and that is now moving this gelatinous material that now actually triggers these hair cells to bend, that now sends a signal to your brain of, oh, we're facing this direction. So those would be your otoliths. Now watch some videos too on the dizzy bat game too. And with the dizzy bat game, when we start getting this gelatinous material to like move all over, this is where some people end up having a really hard time maintaining their balance. Now, when we talk about your dynamic equilibrium, this is all inside the semicircular canals. Again, we have this endolymph, and this endolymph moves with us. And so as it moves, we have these nerve endings here that are going to move with that particular motion in order to send a signal to our brain that we are moving in what direction we are moving. So again, watch that dizzy bat game. When we get this endolymph moving, well, then it sometimes then confuses the brain. Now, when we do talk about equilibrium. With equilibrium, some of you guys get to experience, and I apologize if you experience motion sickness on a regular basis. With motion sickness, how we detect motion or how our brain detects motion, there's actually 3 different ways. It's not just the semicircular canals that your brain uses to detect what our motion actually is. Our eyes are constantly sending a signal to our brain on what motion is happening. And then also we have other receptors throughout our body called proprioceptors. And those proprioceptors, as we're moving, those are also sending a signal to the brain too. So when somebody ends up experiencing motion sickness, it is usually because there is a confusion in the signals. What your semicircular canals are sending to the brain versus what your eyes are sending versus what your proprioceptors are sending are now creating a confusion in the brain that can now result in this anxiety, an increase in stomach acid, and this feeling of discomfort that can actually occur. So how many people who are driving in a car get motion sick? None. Because if you're the driver, now your eyes are matching what your semicircular canals are actually saying, and then also your proprioceptors are also feeling the motion too. So if you get car sick, be the driver. And lastly, on the activities page, there are some videos for you guys to watch. This is actually pretty remarkable when we actually do talk about the loss of hearing. So with people who are deaf, and recognizing that this detection, cochlear implants are pretty awesome in giving people who choose to now be able to hear. It's actually an external cochlea that then sends a signal to the cochlea and to that nerve. So the brain can actually detect these different sound waves that are occurring around you. So that is going to wrap up our discussion on hearing and equilibrium. So with that, finish the activities from the activities page about that, and I will see you for one more lecture for this chapter. So anyway, hopefully you guys are having a good break and you're enjoying some of these activities that we are presenting for you during our distance learning. Miss you guys.